I posted lab. So it takes around 20 minutes to do this lab. I don't want you to do right now. I just want you to have some idea. So in chapter on wave properties of light, you learn that light has a dual property. It behaves as particle and it behaves as a wave. Okay, so when we deal with moving light from one medium to another medium, it could happen interesting situations. So light could be reflected from the surface. So you see, like if you make it normal, like a line that is perpendicular to the surface, so angle of incidence equal angle of reflection, right? So some light could be reflected, some light could be refracted. Okay, so flat simulation for physics are actually very nice because they show that if you will change the angle, so light will behave interesting way. And you can modify, you can have material, air, wood, glass, some substance. And second substance is also we can change. Okay, for example, glass. So when light goes through the glass, okay, so some light will be reflected, some light will be refracted. This protractor you can drag to measure the angle. Okay, angle of incidence, angle of refraction, right? And coefficient index of refraction will show how speed will change when light goes from one medium to another medium. So it's basically ratio of speed of light in one medium, and medium it's substance, so where it travels, air, liquid, glass, like any substance. Okay, so we can increase, or okay, we can decrease n, or we can increase n. So if you'll try to make n equal to 1, it means from the ear to ear, light is traveling and angle will not change. But when you will go into more dense medium, so angle of refraction will be larger and larger. So in glass, it's like big angle. Okay, if you put, okay, that's water. And to find critical angle. When it's critical angle, it's light will go parallel to the surface. Okay. So instruction for this lab is on Google Classroom. Just will show screen. So show one screen and then another screen. Okay. Yeah, so it's basically a unit on wave properties of light. Okay, so it's basically in grade 10 in science you were dealing with refraction of light and total internal reflection, and in grade 12 physics we are combining all properties of light. Okay, so this little lab, it's basically interactive activity JavaScript, so path bending light. So worksheet is posted already on Google Classroom, but I don't want you to do right now. It's later. So it should take around 25 minutes to go through all those properties. That lab, yeah, it's here. I will add link. Okay. Yeah, a link for refraction and this picture. I will try to add into chat. So that link on YouTube, it's basically, remember I was recommending to use a website on physics. Okay. Okay, so to scroll through, like what you will see that, okay, just let me know if whenever I change screens, it disappears, because it happens. Okay, so basically you can go through a review of grade 10, like, yeah, so light goes through another medium, angle of incidence will not be anymore equal to angle of reflection here when it was one medium. So angle of reflection will be different, depends where it goes. So it goes to more dense environment, it's less dense. It goes to less dense environment, the angle of refraction will be bigger. Right? So try to think about traffic. It's easier to go through empty highway than when there's too many cars around. Okay, so different substances have different index of refraction, because what is n index of refraction? Ratio between speeds. So what you will do in that lab, you will basically measure angles and compare some variables. Okay, so here just some examples how to calculate using Snell's law. So Snell's law is telling that n, it's that number, ratio between spin. You can write this ratio as here, n1 divided by n2 equal sine of theta 2 divided by sine of theta 1. And when you crisscross, because it's proportion, you'll have that ratio. n1 multiplied by sine of that angle equal n2 multiplied by sine of the angle. Okay, so the bigger wavelengths, the smaller n index of refraction. Okay, so on Google Classroom, just I will show what it looks like. It's bending light, fat lab. Okay, so again, it's a very, very short activity. You will do it later. At first, I want to go over questions how to solve problems on light. So what I reminded before. Okay, so copy, make pictures, make notes, but I will go fast through those questions, and something similar you will have on assessment on wave property of light. Okay, so you see, for that light, you will make pictures, you'll do small calculations, and then upload your lab to Google Classroom. Okay, so it will be assessment, because we need to have 10 assessments. And when you were working with Mr. Christopher, I didn't notice anything that we can submit to show as work. So I need to submit more work. So, and labs. So labs that are properly written. So I attach Kami program. So you will be able to write it. So don't email to me, don't send pictures. So it's impossible to write on picture marking. So only when it's on Kami, so we can put some comments, evaluation, and anyone who will be checking will be able to see that, yes, it's accessed and it's properly done. Okay, so on your Google Classroom, you will see guide how to use Kami. So license is embedded there. So it will be installed right away. And bending light, Fat Lab, it's your 2 pages, what I was showing here. Okay. Okay, now I will go to questions. Okay, and then he will do assessments. Okay, just at first I will share my file. Okay, so Basher shows, okay. Where is our third student? Okay. Okay, so I'm reminding, so take some notes or screenshots. It will be easier for you. Yeah, those students who didn't know about on physics, the video, link is in the chat. So it's a very good resource. Okay, so I posted this link, refraction, total internal reflection, and that lab is in your file on Google Classroom. Okay, so what you need to know about light. Okay, so let me know if it's hard to see. So maybe I will make it a little bit bigger. Yeah. Yeah, so Young was making a double slit experiment. And what did he notice comparing to single slit diffraction? So 2 lines, and here single slit, 1 line. So in double slit, maxima equal widths, and intensities will be remain constant, fairly constant. So intensities like maximums. For single slit, central maximum twice as wide as the rest. Okay, so it was not symmetrical curve. So if you remember single and double slit, so for double equal maximum, but for single peak, like maximum is like parabola, so highest maximum, twice as wide as the rest. Intensity and each maximum decreases as you move away from the central maximum. Okay, polarization. We can make 4 ways. So if you will need to mention 2 ways and explain how they occur. Okay, so you have 4 different ways. So if you'll select like 2 ways, reflection and filters. So what happens during reflection? How they occur. So light polarized, parallel to the surface. So you heard about polarized glasses, right? So effect is used there. And for filters, plane polarization, so selective absorption. Okay, so for filters, you need to turn under certain angle to see the picture. Okay, so selective absorption, only under certain angles it absorbed. Explain why exposure to ultraviolet radiation is more dangerous than exposure to visible light. Okay, so energy of light increases as frequency increases. Okay, the bigger frequency, the bigger energy. Try to think like excited electrons. Ultraviolet light has a higher frequency than visible light, so it has high energy. Okay, so you know electromagnetic spectrum, right? So high frequency, high energy, and usually those those waves that have high frequency, like X-ray, they have bigger frequency comparing to radio waves. Radio waves have bigger wavelengths, but X-ray have small wavelengths but bigger frequency. So energy of ultraviolet energy can cause damage in ultraviolet to human body tissue, resulting in sunburn, skin cancer, cataracts in human eye. Okay, because high energy particles could destroy humans' tissues. Okay, theory of the particle nature of light proposed by Isaac Newton was accepted by many physicists. Okay, and Newton was able to explain maybe many behaviors of this theory. Okay, and any of his theory we can use as he was counting that light is, he was describing light as particles and which postulates he can use. Okay, so you can use any of those terms and how it behaves, like reflection. Try to think about tennis ball. Hit on the floor, reflects back. Refraction. Okay, goes from one medium to another medium. Also it's like straight. Dispersion, propagation, diffraction, partial reflection, refraction. Okay, so how to solve problems? It's like thinking problems, application problems. 2-point source interference pattern is generated in a swimming pool. Okay, so a piece of styrofoam, and we have second nodal line, distance 12 meters from one source and 20 meters from other source. So one wave crest makes 2 seconds to travel these lengths. Find the speed, wavelengths, and frequency. Okay, so speed V. Like whenever you have any questions, it's better to write what is given, which is required, formula substitution. Frequency is F. So you learn about wave properties from grade 11, so it's basically the same. So how to get speed, how to get lambda, wavelengths, how to get frequency. Okay, so because it's second nodal line, so difference between 2 points is wavelengths multiplied by n minus 1/2. So you plug those values that are given, 12 and 20, and you will rearrange, find what is lambda. Right? How to get speed? So it moves with constant speed. So distance over time gives you speed. So what is distance? It's those 35 meters. How long it took? 2 seconds. Right? So distance over time gives you speed. How to get frequency? So use universal wave equation, frequency equal speed over wavelengths, and you will get frequency. So don't forget all these units. So frequency we measure in hertz by Henry Hertz. So velocity in distance over time, meter per second, and wavelengths in meters. Okay, so I'm sure you have this. Okay, second one, blue light with wavelength. So lambda, nana, it's 10 in power negative 9, right? Yeah. So whenever you use prefixes, okay, always change into proper lengths. So C unit, meter, kilogram, seconds. Double slit with separation, micrometers. Okay, so 22.6 multiplied by 10 in power negative 6 meters. So micro is 10 in power negative 6. What is the maximum number of model lines visible in the pattern? Okay, so you need to find n. Okay, and light goes perpendicular to the surface. Okay, so sine of the angle equal wavelengths divided by distance multiplied by n minus 1/2. Okay, so you need to rearrange for n. So how to do it? So multiply both sides by d, divide by lambda. So you're getting rid of this coefficient. Now you can move n away from 1/2. So basically negative 1/2, you move to other side and plug your values. Okay, so it will be 96. So you need to divide by 2. So 48 on left side, 48 on right side. Okay, so I'm moving now to the next picture. So be sure you scroll. Saved. Double experiment is performed using slit separation. Okay, so distance between 2 lines, 0.12. Okay, it's your D. With a screen placed 80 centimeters away. There are 18 millimeters between first and seventh nodal lines. Okay, so you see 1, 2, 3, 4, 5, 6, 7. So 18 millimeters is distance between first and last. Right? What wavelength light was used in nanometers? Okay, so because it's very small length, right? So you need to find wavelengths. Okay, so you write what is given. Okay, so what is the distance between them? Between first and seventh, it's 6 distances, 6 delta x. So it's 18 millimeters. How to get delta x? Both sides divided by 6. So 3 centimeter. Okay, so it's 3 millimeter. Okay, so here it's actually it's not 3 millimeter. It's 0. Okay, so it was millimeters, right? Okay, so units here. Why it's 18 divided by 6, it's 3 millimeters. No, it's not 30 centimeters. Okay, so this one is not. Okay, but just try to get idea. So 3 millimeters and turn millimeters into centimeters. Just think 1 centimeter is 10 millimeters. 18 divided by 6 will be 3, yeah, 3 millimeters. So it's 0.3 centimeters. Okay, and then ratio between delta x and distance to that source equal wavelengths divided by distance. So what we do, we multiply delta x, okay, this one properly, 0.3, by d, so 0.12 millimeters. Okay, so here, because everything is in millimeters, yeah, so you don't need really this one to use. So we are using millimeters, millimeters, millimeters. So what will be at the end? Okay, millimeters gone. And what is 800? Is it 80 centimeters? It's 800 millimeters. It's, yeah, everything is right. Okay, so distance will be in millimeters. Yeah, because you see millimeters or millimeters will be gone. So in numerator, it will be millimeters. And how to turn into nanometers. Okay, so millimeters, it's 10 in power negative 3 of meter. So 10 power negative 3 and 10 in power negative 4. So you add exponents together, negative 3 and negative 4 gives you negative 7. So 4.5 multiplied by 10 in power negative 7 meters. Okay, nano is 10 in power negative 9. So to turn in power, so divide by 100, one part, right? So divide by 100. So you multiply by 100 this part. So 100 multiplied by 4.5 multiplied by 4.5 gives you 450 nanometers. Okay, so it's transformation from one unit to another. Okay, number 4. Oh, okay. One sec. Diffraction grading. Okay, use a slide with a wavelength. Okay, so it's lambda, so many nanometers. So nano is 10 in power negative 9. To generate interference pattern, if the highest order maximum appear on the 5th order. Okay, highest when angle is 90 degrees. What is the line density of the grading in lines per centimeters? Okay. So how many lines? It's frequency basically. 1 divided by d. So sine of the angle equal, and we have that formula for m. How many lines? 5th order. Look, 5th order multiplied by wavelengths. Okay, and divide by d. Okay, and that d we need to find. Okay, so to rearrange it, you divide numerator by what you have on the right side. So you have 5 5th order wavelengths you plug here, and it's perpendicular, so sine of 90 degrees gives you 1. So distance we found. How to get line density? 1 divided by that amount, and you will get how many lines it will be per centimeters. So it's like frequency, how many lines through that little area. Okay, and question 5. High-end optical instruments such as SLR camera will have an anti-reflective coating. Okay, applies to its lens to decrease the amount of light lost to reflection. Since the camera is used with white light, the coating is usually chosen to create destructive interference, usually it's darker, for wavelengths near the middle of the spectrum, so many nanometers. A layer of titanium nitride, index of refraction 1.2, you see it's bigger than 1, is used as a coating on a glass lens. Index of refraction 1.65, so different n. What is the minimum thickness of such a coating? Okay, so light will go through the ear that has n equal to 1 to the film. So film has index of refraction n 1.2 to glass. So glass has 1.65. So 2 phase changes. Okay, so refraction, refraction, refraction. Wavelengths near the spectrum is 555 nanometers. So nano is 10 power negative 9. minimum thickness. Okay, how many? Okay, so twice distance for destructive interference. Okay, because waves should cancel each other. So twice distance equal wavelengths multiplied by n plus 1/2 divided by n of the film. Okay, so we plug our units, we divide both sides by 2, so the diameter will be twice bigger, and it will be that length, so distance, so small in meters. How to change it in nanometers? So nano is 10⁻⁻⁹. So you divide by 100 this part, multiply by 100 the base. So when you multiply by 100, you move dot 2 places to the right. So 115.6, you can round till 116 nanometers. Okay, so be sure you have it. Yeah, and we are moving to next question. Okay, light from monochromatic source passes through a single slit with a width of 12.7 micrometers. Okay, so micro is 10⁻⁻⁶. Right away, it's better to write. If the fourth dark, so n equal 4, fringe appears at the angle of 10 degrees, calculate the wavelengths of the light used. So wavelength is lambda. So what we need to get, right? Okay, so when we have relationship between angle and pattern, so sine of the angle equal n lambda divided by w. Okay, so we need to get wavelengths. So multiply both sides by w divided by n. So sine of the angle, it's sine of 10 degrees. It's wavelengths. It's better to put lambda. Okay, so lambda. Okay, lambda wavelengths. Okay, so it's lambda. Okay, it's widths. Top. Okay, 1 second. Okay, so how to rearrange for lambda? V multiplied by sine. Yeah, V multiplied by sine divided by n. Okay, yeah, it's fine. Okay, so V is that length between how wide is that single slit? Oh yeah. Okay, so here that length, and you have fourth dark fringe, so and divide by 4. Okay, and again, to turn from meters to nanometers, you divide by 100, multiply by 100. So 5.51, when you move dot 2 places to the right, will be 551. So by spectrum, you can tell that it's green light. Okay, so you need to be sure that you understand how to solve those type of questions. Okay, do you need to go back to any of the questions? Just check how many students we have. Lauren, Basher, Hala. Okay, one is missing. Yeah. Yeah, so multiple choice question. Yeah, so how to get index of refraction? So again, index of refraction, it's ratio of speeds in one medium and in another medium. Okay. We need to start somewhere in 10 minutes. Like I will upload the file to solve, because we didn't have nothing on unit 5. So I'm trying to scramble. I expected Mr. Christopher will finish, but okay, so you had independent work, basically. Okay, so index of refraction, it's ratio between speeds. So it will be 1.41. Okay, so did you try to check on your calculator? Okay, so grab your calculator, try to check. Can you see that when you divide, so speed of the light divided by speed of the light in that medium gives you 1.41. So you round till 2 sig figs. So 2, 3 sig figs. Yeah, 3 because we had 3 sig figs here, 3 sig figs here. When we have division, we keep the same amount of sig figs basically. The smallest amount will be the same as for each of them, 3 and 3. When I observe diffraction, okay, in a ripple tank, so increased diffraction, you consider 3 options. Okay, so the best adjustment, a combination of adjustment is, so you want to increase diffraction, so that hole should be smaller. So you need to make it smaller, width of the opening, and make frequency of the source smaller. So when you have smaller frequency, it will be more bending around. Right, so diffraction will be around the corner when you have smaller slit and smaller frequency. So decreasing the depth of the water will not affect. So only first and last. Diffraction by a single slit in a ripple tank can be decreased by increasing the frequency of the source. It's basically, they're related, you see. So you make frequency of source smaller, diffraction will be bigger. If you increase frequency, diffraction will decrease. Okay, this is basically the same idea. 2 and 3. 2-point sources in a ripple tank vibrate with frequency to produce wavelengths so big. The difference in path lengths of 2 sources at the second model line will be, okay, so 3.6. So you have lambda, you have F. Okay, so you can do your calculations. So difference in paths will be 3.6. Okay, so 2-point sources, 4.5 centimeters apart. Okay, it's distance here. Are vibrating in phase as a ripple tank. You count exactly 10 nodal lines. Okay, so exactly 10 intersections. It's dark spots. Approximate wavelengths is okay. So here is D. Oh, it's not really okay, but it's the same idea, the same picture. Here's the next one. So 2 points are vibrating. You count 10 nodal lines. What is wavelengths of the water tanks? So it's like 1 centimeter between. Okay. You observe the water pattern in figure 2 as you investigate periodic waves in ripple tank. You draw the straight line through superimposed on the picture. The wavelength is, okay, so lambda will be x, so that distance, multiplied by d, so distance between 2 sources, and divide by twice the hypotenuse. You can think because it's perpendicular. Okay, so xd divided by 2l. Okay, you wish to continue the same pattern as in question 6. Okay, 6. But contemplate making adjustments. Okay, so you have 3 options. Okay, you need to increase the number of nodal lines. Okay, so to increase number of nodal lines, okay, first and second will work. Okay, to increase n, you need to make higher frequency of the source. So increase the frequency, will be more nodal lines. Okay, increase separation of the sources. So put those sources away from each other. It will be also bigger amount of nodal lines. Okay, so first two will help it. Adjustment or combination of adjustment in previous question that result only in a shift of the nodal lines is combination of adjustment in question 7 results in shift of nodal lines. Okay, so shift of the lines will be if you will not start at the same time those vibrations. Because what is wave? Like wave needs to have source of vibration. If you don't start at the same time, if you have phase delay, then it will be shift of the nodal lines. Okay, so only phase delay in one of the sources. Particle theory is unable to account for the phenomenon of interference. Okay, because particle theory, like think about like a little ball that will be thrown and reflected from some surface. So you can apply for reflection, for propagation, go straight line. So it's motion along straight line. Emission, so go through. Okay, radiation pressure, but yeah, interference. It's not particle theory. Interference, it's wave theory. Statement regarding Young's experiment that is false is okay. So interference pattern from this experiment has a nodal line down the center of the pattern. Okay, so sometimes it's easier to check like what is for sure is true. Yeah, so diffraction will be in both ends. Phase will be the same fixed when it moves from one and another opening. Separation dependent on wavelengths. Wavelength depends from frequency. Particle theory was unable to give a satisfactory explanation of this phenomenon. So particle theory. Yeah, because that's why we have dualistic theory for waves. So particle theory and wave theory. So light is unusual. It has both properties of light and particle. Okay, so you got the idea, right? Yeah, so I was planning at after 145, 150. Okay, so you will do assessment on light. So I inform you, like try to review light. Okay, I will upload in a couple minutes. Okay, so try to look where is your calculator, where are your resources. Just need to upload on Google Classroom. Just a reminder, you have Kami, complete on Kami, and write it properly. It's easy. Or print and upload, but upload only PDF file. I don't want to see any screenshots. Screenshots impossible to mark. So I'm doing a little bit formatting. And I will upload in a couple minutes. Okay, I'm saving now as PDF format. I will upload in 1 minute. Okay, so guys, get ready. So prepare your calculators. Look at formula sheet, like it's a basic formula you're using from the beginning of the course. Use your textbook. Okay, test with nature of light. Okay, I'm uploading now. And lab you will do after, like, I don't know, it's like your homework. Basically, it's practice. It should take less than 20, 30 minutes. Yeah. Yeah, so please open your Google Classroom to be sure that you can see it. So Kami instructions attached there. So if you didn't use it before, start using. Okay, I can share a screen. Yeah, and while you're doing, I will be checking what you have on your Google Classroom. Yeah, because I asked to upload whatever you didn't complete before. So we're close to the end of the course. I uploaded before New Year summative. Oh no, summative I uploaded on January 3rd, early morning. Yeah, so I hope you're working on it because it should be submitted on Wednesday and it should be with your voice over. So an all option, everything is written there on Google Classroom, how it's supposed to be. And on Friday is exam. Okay, so summative. Okay. Summative is due